Explosions are among the most dramatic chemical events we can witness. Sudden flashes of light, powerful shock waves, intense heat, and rapidly expanding gases. While they may look like pure chaos, explosions are actually governed by precise chemical rules. At their core, explosions are about energy speed and molecular rearrangement. Understanding the chemistry behind explosions helps us not only appreciate their raw power, but also learn how to control them safely for beneficial uses like mining, space travel, medicine, and even entertainment. Chemically speaking, an explosion occurs when a substance undergoes a very rapid exothermic reaction, releasing a large amount of energy in an extremely short time. Most explosions involve molecules that store chemical energy in unstable bonds. When triggered by heat shock, friction, or an electrical spark, these bonds break and reform into more stable molecules. The key difference between an explosion and ordinary burning is reaction speed. A log burning in a fire releases energy slowly, an explosive releases the same type of energy almost instantly. One of the most important concepts in explosion chemistry is oxidation. Many explosives contain both fuel and oxidizer within the same molecule. This means they don't need external oxygen from the air to react. For example, compounds like TNT or nitroglycerin already have oxygen atoms tightly packed into their structure. When triggered, the fuel and oxygen react internally, producing hot gases such as carbon dioxide, nitrogen, and water vapor. These gases expand violently, creating the blast. Another critical factor is gas formation. Solids or liquids that rapidly turn into gas create enormous pressure. Imagine converting a solid into thousands of times its volume in gas within milliseconds. This sudden expansion is what generates the shockwave we feel during an explosion. The faster the gas forms, the stronger the explosion. This is why some reactions burn, some deflagrate, and some detonate. Chemists classify explosions into two main types: deflagrations and detonations. Deflagrations spread through material at subsonic speeds driven by heat transfer. Fireworks and gunpowder fall into this category. Detonations, on the other hand, involve a supersonic shockwave that compresses and heats the material ahead of it, triggering the reaction instantly. High explosives like RDX operate this way, making them far more powerful. Temperature also plays a crucial role. Explosive reactions can reach thousands of degrees Celsius in microseconds. This intense heat causes surrounding air to expand rapidly, forming a blast wave followed by a vacuum like drop in pressure. That pressure difference is what shatters windows, bends metal, and causes structural damage, not just the fireball itself. Interestingly, not all explosions are destructive by design. Controlled explosions are used every day. Car airbags rely on rapid chemical reactions to inflate safely in milliseconds. Rockets depend on controlled combustion to generate thrust. Even combustion engines are essentially managing tiny explosions thousands of times per minute. In chemistry labs, scientists study explosive reactions carefully to understand reaction kinetics, energy transfer, and molecular stability. Explosions also teach us about chemical stability. Some molecules are stable for years but can become explosive under the right conditions. Others are so unstable they must be handled at extremely low temperatures or diluted forms. This balance between stored energy and stability is one of the most fascinating challenges in chemical science. In nature, explosions occur too. Volcanic eruptions, supernovae, and even seed pods that burst to spread plants all rely on rapid energy release. On a cosmic scale, nuclear explosions follow different rules involving atomic nuclei instead of chemical bonds, but the visible effects, light, heat expansion, are surprisingly similar. Understanding the chemistry of explosions isn't about glorifying destruction, it's about respecting energy. The same chemical principles that can cause devastation also power human progress. When we understand how atoms rearrange, how energy flows, and how reactions accelerate, we gain the ability to control nature rather than fear it. Explosions remind us that chemistry is not just equations on paper, it is force, motion, heat, and transformation happening at breathtaking speed. Every boom is a story of atoms seeking stability, releasing energy, and reshaping the world around them in an instant. If you enjoyed this deep dive into the chemistry behind explosions and want more science explained in a simple, powerful way like the video, share it with curious minds and subscribe to the channel. Science becomes even more exciting when you understand what's really happening behind the scenes.